I'm Yasemin Askari, a student from Computer Science ONS de Lyon. So I'm going to presenting how I just come over my project on the 3D geometry. So we had a exercise on 2D geometric representation, and we used Cybran for that. And then we just as I can show you some of the results, you can see that we can just learn a sine distance function for a circle and also for a square. So as a project, I just come over down and then I started doing the 3D point clouds. So as you can see here, it is very big as we can start the project, and it was something like, let's start reading that. A natural extension of this exercise is to fit an implicit surface over 3D point cloud. So first of all, I didn't know what was the point cloud and also what was implicit surface. Then they said that, okay, we should extend the 2D functions, and then we need to display the zero level set. And I didn't know what is a zero level set too. And then, okay, it's a 3D surface. And they said that you can extract the triangle mesh of zero level set using marching cube algorithm. Still, I didn't know about what is actually marching cube. And then we wanted to just convert the implicit surface to a mesh. And it wasn't that much clear for me, but there are some references for that. One is for the marching cube. It is coming from the Wikipedia. Let's open it. The problem of the internet connection is going to be very bad sometimes. Okay, it says that it's a computer graphics algorithm introduced in 1987, very old. So it's coming from SIGGRAPH. It's a very great conference on the somehow graphics learning. So it's an algorithm, and it was somehow telling us about that, but not that much information on this. Okay. Then there is another one, marching cube in scikit image. Scikit image or skimage, it is very important for our work. It says that we can just induce these graphs from that library, and that's ellipsoid. So not that much, so I don't know what are these things. And then just come over the SDF as simple shapes. Everybody recommend this one, and it's a very great page on the SDFs. And there is also very great video tutorials. I really recommend that you can see those things. But what we can see here is a sphere, a box. There are multiple meshes. Sine distance functions. So we can see that all over. Again, there are a lot of things here and here. Okay. Perfect. So if we need a sine distance function, we should use this website. But first of all, what is a sine distance function? I don't know. And then it says that there is going to be another link from the professors, starting by going to be somehow a Google Colab web page using TensorFlow graphics and 3Mesh. So let's run this code. Let's see what is going to happen. Okay, we are going to just first of all go for the installation. I just did something wrong. It will cause an error, so it doesn't know 3Mesh. It's not yet installed on the Google Colab. So it's going to be installed very fast in the Colab. Okay, perfect. Now we are going to just, somehow import the libraries that we installed. One is TensorFlow graphics and another is 3Mesh. So let's do this later, but we can also understand this. Okay, perfect. You can see that we can just move this river. Okay, perfect. So It's going to be super good when we are going to do a visualization, but I'm not yet sure that how we can use it. So this is a project that I was proposed to do, and mainly, for my 50% of the course score. So let's just start doing this project and see how I just completely did my slides all over this work. These are my slides. So let's start with 3D geometric representations. Okay, we should do 3D with the siren activation. So what is siren paper? Let's go over it. There is, 719 citation, so it's a very great paper. So let's go over the archive version of it. We just go over downloading this. Okay. So it's 35 pages. We do not have time to read all of those things, but I would like to just scroll it down. And it says that, some functions here, but I don't know what are these functions. So it's just tell us about some pictures that are going to be better than the value in the machine learning, or maybe 10H recording the grand truths. These are the grand truths. And you can see that this siren is much better than the ReLU with the positional encoding and also 10H and other things. So we yet do not know about these things. So loss functions, some these things. And okay, it says that if we use these grand truths and use siren, things are going to be very good, but ReLU is not going to be very good. Okay. And also it says that it's good for Poisson blending. Not yet. Okay, this is what we want. We are going to have the shape representation. So we are going to have 3D shapes, and then we are going to fit sign distance functions by implicit neural representations on the point clouds. So first of all, I read this one and I said that, okay, what are sign distance functions and what are implicit neural representations and what are point clouds? And they said that it's going to be a ReLU. So first of all, it's going to help us a little bit. And nothing more on this paper about these things. Yeah, I didn't see anything interesting, a lot of mathematics, but nothing more on the 3D representation. So it says that it is only really better than the ReLU, but I don't know why. So we should go over on another direction. So we just go on the videos, and there is a video, so we click on that. Okay, there is the web page of the paper. It's very usual that every, paper in this graphics learning or computer vision or image processing, they are going to have each of those things. They are going to have, somehow a website, and they are going to have their paper, collab notebook, and also code and data. So we have the code. Maybe we can cheat that thing and maybe write down our codes based on a collab notebook. So let's see. Okay, let's see that video together, but not that much together. Okay, I would like to just tell you that it's going to be good. So first of all, this is going to be really nice because it's going to introduce you what is a ReLU MLP and what they are going to do as a sign one. Let me go over there. Yeah, here they are going to be something like a sinusoidal representation networks. So they said that what we are going to just use the ReLU MLP with the sign activation. So, okay, let's start by this paper. It says that we are going to have discretization over images, shapes, and the audios. And it says that also there are some types of discretizations that they are going to be a main drawback for that we cannot, just upsample it or make it higher resolution because we do not have enough information. So that's all. We should just watch this video. If you want, you can just come to the web page that we have, they have, and also watch this video. It's going to be very motivational for you. But let's go what we have here. It's going to be very nice. These results are very nice, but you know, it's going to be loaded, but you know, it's going to be similar to the paper. Okay. Everything's fine, but you know, let's go to the collab. Okay, everything's crashed. Okay, now it's okay. Okay, let's start. Okay, we just go over the collab notebook. And it says that, okay, you can see a lot of things here. So you can see some code, some cyan layers. It is very similar to what we did on the 2D. And then we just come down and we do not see anything that is going to be 3D. Yeah, nothing 3D here. So let's close this and go to the code. Okay, it's going to be on the GitHub. It's going to be loaded. While loaded, I said that usually it's not really good to go over the packages that actually paper is going to write them down, but you can see that it's going to be very popular. 210 people just worked it, and also there are a lot of stores and people are watching it. So there is an idea that you can just go over these functions and try to code it by yourself, but you can see that they are not that much, you know, on the 3D. I didn't see that much on 3D. You can see that some the loss functions, explore assignment that we saw that, SDF meshing, not that much. And also I do not see that much of good things. Let's see, can we see something? These are for images. There are some for videos. Yeah, and these are also for images and for the videos. So, and also for the meshing. Yeah, it's going to say that SDF is going to be polygonal using the skimage marching cube. So we can now see that marching cube is going to happen, but not that much code on things. And we do not know that. So can we see some data here? Yeah, nothing here. Yeah, nothing here very special, nothing, you know, just something like the SDF meshing are going to help us, and also the network. I didn't see the network here, but you can see this, I think. This is the, you know, training part, but not that much on this code. So it's not really a good idea to work on the web page. So one another idea is that you should start reading the forks, view existing forks, and there are a lot. So it's not time to just explore all of those things, but usually people fork these things and do not add anything to it, no explanation. So it's very hard to go in this direction. So you should do another thing as I did, and I just close everything one more time. Nothing special about the paper. So these are some first of all videos, but we are not familiar with sign distance function and other things. So we are going to start by the other things. Okay. So what we are going to do, first of all, we are going to just go over my slides and find some of those resources that I used for my work. Okay, so it's going to be somehow, yeah, this is going to be a really good video, but I'm not going to focus on that. Yeah, this one is a really good one. I'm going to just click on that. Okay. Searching on the internet, you're going to just find some great resources on everything. So it starts just talking about neural implicit representations for 3D shapes and scenes. And it has some keywords in it that are going to help you. Some is deep SDF, so it's going to be maybe a really good one, and shape surface reconstruction. So you go over the introduction and you can see that you can find a timeline for these works, and people are going to represent shapes within neural network, and then we're going to represent scenes and also understanding and also making faster things. So this starts with a brief background. So these are going to be really good. First of all, it just talks about ray tracing and rasterization for rendering. So if you're not familiar with these things, just I would like to tell you, go over these things and learn about that because they are very necessary for our work. Then we have the 3D geometric representation. It says that we have multiple things, meshes, voxel base, and point clouds. And for each of those things, you can find, first of all, a Wikipedia that you can explore. So I did, and I know a little bit about these things. So it's going to be super nice. Then you're going to talk about watertight and non-watertight. So it says that it's going to be something like topological constraints. So watertight surface is going to say that, okay, if you are going to pass the water through it, it's not going to be inside it. But non-watertight, they are going to say that, okay, if you pass water through it, it's going to pass water from inside it. So let's go back on my slides and tell you till now what are our information. Using the paper of the Soren, we know that the real-world data is not discrete, and we understood that the drawback of this discretization is going to say that it's going to be, a discrete amount of information regarding the signals, and reading that GitHub page from that person, we are going to understand that it's going to be point cloud, voxel, and meshes. And now you know all about these types of it and advantages and disadvantages. Okay. We finished with this here, and it says that we are going to find these representations. And there is, implicit representation. So we just click on this. And we go over the Wikipedia, and we understood that there is going to be a function that's going to represent the surface that we have. So it's going to be 0 level set. So now we are going to learn more about what we had here. Then it just talks about sign distance function. And these are super nice. So now we know about the sign distance functions. They are going to say that, okay, if we have a surface inside this, it's going to be negative values. Outside this, they are going to be positive values. Okay, let's click on this link also. Maybe it has some good information. Sign distance functions. I think that it has too much mathematics and not much information. So I'm going to tell you that there is another one on resources that you can see that there is a medium. Mediums are really good, but you can just go over maybe 10 of it. I don't know. It's very limited access to the medium, but you can just use it. So what is the sign distance function? You can go over this. So you can find some properties of the SDF. So one of the properties is that the gradient vector, norm of the gradient vector is going to be 1. So as we saw on the TP, it's going to be similar to this one. And then what we say that there are some properties that are going to help us with raycasting. So it does help us with these some examples, and they're really nice. Then what know we now about the sign distance function? So let's go over whatever we know now on the slides. So we started by discretization, and we said that if we can find a function that represents our data, it's going to be very nice. There is going to be a video that explains this that I'm going to say. This is by Wisman. It's a 1-hour explanation of the Soren paper, and I just put the link on the resources. So it says that some continuous functions are needed to make these functions that they are too complex, that we cannot write them down using by MLPs, multi-layer perceptrons. So we are going to just go and say that we are going to learn a function using the XYZ values and the value of the function on that, maybe we are going to say, and the gradients and the second order derivatives from the domain of the XYZ to that surface. And we know from reading some of those videos that I just mentioned in the GitHub of the paper, you can see that there's some applications to the robotics, simulation, content creation. From that another page, we know that it is agnostic to grid resolution. If we are going to have more and more complex signals, we are going to just use model memory more. And then we are going to just say that the differentiations are going to be computed automatically. Because of using the MLP and using gradient descents and all of those things, they are going to be very easy to find the differentiations easily. Then we learned about the sign distance function. As I told you, it was a great explanation of sign distance functions. And I said to you that we have points inside the shape, they are going to have negative values. Points outside, they are going to be positive. You can see them by blue and red. And then we said that the implicit surface, this one, is going to be the zero level set. It's going to be sign distance function has these zero values. Maybe you can see these 2D implicit surface or maybe sign distance functions from your geometry class, geography class. Before that, you can just find the maps of mountains easily. But now we are going to work with the 3D. I just got these two images from a paper that I just read it later on ISDF. So we are going to introduce it later. Okay, so and then I started just working on the properties, as I told you, that it's going to be that the norm of the gradient is going to be always 0 and other properties that I told you. So now we have half of our way, and now we are going to start learning the SDF. So let's close all of those things. We know already about it. Okay, let's close this one. And also, okay, just read carefully these things because these are super nice, and also about implicit representation. So we had now a keyword. It's going to be deep SDF. Okay. We go over the paper. It's going to be 1447. So super nice paper. Let's start over it. Is it going to have a web page? Usually it has. So let's go over that to open this. Maybe we can find it also here. Yeah, these are some codes. And nothing more. Yeah, nothing more, I think. That's all. So we know that Siren paper is going to be only, if we have these functions for the 3D of the deep SDF, we are going to say that these are ReLU. Now just change it to sign, and it's going to be super good because now we have everything. Okay, we can see great things. Some chairs are learned, and also a class of cars are learned. Super nice. So then we start, I just grabbed that image from here, this one from here. And then I just started reading about also point-based, mesh-based, and also about the voxels. So if you didn't read on the Wikipedia, you can also read these things. It is super nice. So now you can start reading a paper. So you know about all of those definitions, and it's super good. So it is very greatly written. And then we says that, okay, now we have whatever we want. It says that we are going to model SDFs with the neural network. So it explains, and now we can find something good. I grabbed this image from this paper. So it says what? We now have a single shape deep SDF. It means what? It means that if you have X, Y, Z and their sign distance functions values, we just give these things to the neural net, and finally we have the SDF. But what is this thing? It says that if you are going to just find a class of shapes, we are going to have all of those codes, and then we're going to condition on that, and it's going to be very good. Okay, but we just should have a greater step here. Now we know that it's going to be a decoder, or maybe another types of structure of the MLP, but it's going to be similar to the single shape. So it can be also other things, but we do not need that thing. It says that it's going to be really good. Nothing more about this. It's really good. So very nice shapes. And it says that it is going to be very robust. They just added noise to it, and it's also great. So, oh, okay, super nice. We just understood what is deep SDF, and it's going to be very good. Is there any code for that we can learn from this? We go over there, and we see what? We see that there is a code. But look at here, we can understand that the code is in the C and not in the Python. So there is a lot of problems here. So C is very fast, but we need Python. We do not need C because we do not learn about C. But there are some codes that we can use it. Maybe we are going to generate something. We cannot see anything, special. I also did not see something like good. Okay, reconstructing. Okay, nothing. It is only debugging logs. Train SDF. It's always logging these things and also debugging. So it's very hard to read. Okay, but here we have something good. There's a lot of forks. I just click on fork and want to find these existing things. Okay, these are super nice things. Maybe one want to explore as me. I've started just reading one of those things, but didn't see much of work, but I was really happy that there were something. Let me just bring it. Yeah, this one, I think so. Yes. Okay, I just explored those works and just come over here, and I don't know. Okay, there is a calendar what she has done, or maybe he has done. It's going to be super Pythonic. Okay, very nice. So it says that she only puts all over the videos that she had. So I just found all over these videos, and I started just watching these things all over. Okay, we were in the right direction. So now we have the deep SDF, mesh SDF, so it's going to be good. So she explained that we should just do some data sampling. We just come over here and say that there is going to be a package. Perfect. There is going to be a mesh to SDF. So click on that, go over it. Okay, we are going to install this. And now if you have an object, we can just find the point clouds and the sign distance functions. So super nice. It's going to be very good. Okay, it has something like mesh to SDF, and also we can sample SDF near space. So it's going to be nice. But I didn't read all of those things and said that, okay, I will start with the mesh.df and didn't read all of those challenges. But after a while, I understood that I should have read because it doesn't work on the Collab. It doesn't work on the Linux. It doesn't work on the, MacBook. It only works on the Windows. And I think I didn't just had all of those things that she said, but I just had 3 models in the end. I just sampled with 400K points. So it was okay, but more, it just crashed with the memory. So I didn't go over all of those things, but she just gathered a lot of things. And she said that, okay, if you didn't find a lot of things, there is a 71 gigabytes of pre-processed data. So you can just use things. And then I just come over here and find out we can use 3Mesh. Okay, and PyRenderer. Okay, there's going to be PyRenderer to see that thing. And maybe I can just show my Jupyter notebook to you. Maybe not. Okay, I will do that later. Okay, I just used a similar approach and just made a blue color for inside ones, and all for the outside they are going to just be red values because it's going to be RGB. So if you're going to have blue colors, you should just put this one, and if you are going to have red colors, you should put the first channel one. So I use this one, but this is going to be something like the results that I had here. Yeah, here. Okay, this point class I just got from this similar approach that I just got from that GitHub. So it was super nice. Okay, so it was nice. We know now how we can just have a data. Till now, we understood from the deep SDF that we should have a point cloud with sign distance functions. Then we are going to use the neural net to have the sign distance functions, implicit ones, and then we are going to use a marching cube to find our mesh, but we do not know the marching cube, what it is. And then we are going to say that there are some advantages that we find it in the paper. It says that discretization is going to happen in the end part, and we can simply change the topology. We couldn't do that before, and we can learn a class of shape. So we saw that, but we do not work with that thing. Okay, now we understood that, okay, we have a mesh object and our .obj data. Then we are going to load that with 3Mesh, because I saw that here in this one. It says that it's going to be loaded here. So it's a package to load the meshes. And then what we are going to do, I'm going to just say, come over here one more time. Okay, just slideshows. And then we are going to have a PyTorch MLP as we saw in the deep SDF, and then sign distance functions, and using the marching cube that we are going to learn and find the reconstructed. So now we find that PyRenderer is okay, and we knew that TensorFlow graphics is also okay. So Matplotlib was very bad, so we are not going to use that. Okay, perfect. We know already about everything. And okay, this one was finished. We know how to data sample it. And then, oh, sorry. Yeah, I just come over this data preparation. Let's load it. Okay. But I really do not like the way that she just do these things. So So I understood that we should just divide it to train and test, but I do not love that way that she does this. And then we have the samplation, and there is going to be her STF. So she has a simple block, an STF decoder, but you can see that it's going to be leaky value, and it's not what we want. And also 10H, we do not need that. So it's going to be not that much okay with our work. And also we didn't see any results from her. So maybe it doesn't work. So I do not judge it, but maybe it works. But this is not what we want. But it's very near. So we are going to have this code. This is going to help us very well. So let's see what is marching cube. I'm going to bring it from the resources. Okay, it's going to be marching cubes tutorial. Okay. But let's see what is this web page. I think that we should just go over the first article and say that, okay, it's going to be an explanation on the marching cube. It says that if you're going to have a function and we are going to have a polygonal approximation, we are going to use that. And it's going to say that, okay, we can mark some points inside and outside. Inside is going to be black, outside is going to be white, and then we are going to find a boundary. So now we are going to have 16 combination of those, and using this combination, we are going to have our approximation. So it's nice. Good. So now we are going to do the 3D one. 3D was super nice. So we can see that it says that, okay, we are going to have 256 different cases, but using some tricks that rotating and mirroring, we can just induce it to 18 cases here. You can see that. And then it said that in the Wikipedia that the professors that let me know about this, they said that we only need 15. So, so we should just take care of that. And that's all. So it says that there are also another technique, it is dual contouring, but we do not need that thing. So first of all, now we are going to have the 3D marching cubes. Let's go over here and tell you that I just put informations that I just got from that web page. So now it's complete. And now I should just use the deep STF of that girls and another web page that I just found. But, you know, there was a project that someone did. I used some of slides during that, or if I can find it. I don't know. Okay, maybe not. There are some slides here. Maybe I cannot find them. Okay, let's do that later. It says that maybe some results are not going to be good. So we just really expected that. And we just use our code on the TP3 geometry and some of the code here in the deep STF and combine all of those things, and then we found some results. But our journey is not complete here. We should just make some challenges that we faced. So it's nice. But we should just represent some future works. Searching through the internet about 3D sine distance function, I just found a web page of the dataset and explorer for 3D sine distance function. It has a really great dataset. Let me show you some parts of it. Okay, it's going to be that sample. Yes. It's going to be here, surface. You can see some samples. And also this one, also some samples. If for each of those cases, there are going to be 2 million. And also for the near one, 2 million each of those things. So it's going to be a 4 GB, I think, data set. Let me bring you the web page. It's going to be STF Explorer. Okay. Okay, this is going to be the paper. And also some data sets that they provided. You can see all of those is that they are there. And I just brought those pictures from here and also other parts. So if you are going to learn about the paper, just go over this video part and learn about that. It's good. And just looking at the paper, I understood that there is another data set. It's going to be Thinking 10K. It's going to be have 10,000 3D printing models. So two questions come to my mind that we should just go over. The ISTF. It's going to be, real-time application of that. You can simply go over there and see what can be. It's going to be end of the video. Okay. You can see the ICF, there is a video, there is paper and code. You can see the explanation. It's really nice. And you can see that it really works for the robotics perception. And you can find out these sign distance functions real time. It's really nice for the robotics. So now what I got from here as applications of that is going to be added from that board. So it's going to be on a paper of RSS 2022. And then it was in my mind that do we have multi-layer deep sign distance function learning? It was in CVPR 2022. Let me show you that thing too. GIFs or GIFs, I don't know. So GIFs are neural implicit functions for general shape representation. It also has a video. It's super nice. And you can see that there is a really good GIFs. And also you can see the video and the representation. So I've just brought those pictures and GIFs from these parts. So now my slides are complete. And then I just found some story for that. I'm going to say that it was a really nice journey. But if you are going to have, a project on the deep learning and also, geometric one, there is a huge amount of resources. You can see on my slides. I'm going to put it on the comments and also on the description. So these resources are accessible. But usually, please try to not cheat the codes that are there. So please try to sample the codes and understand what should you do. So we already understood how we can go over these papers and understood what are those things. So that's all about on my project, and we can finish it here and go over the code that I just posted on my GitHub and also on the presentation resources. Is going to be super good. Bye.